Real quick review of what we've done over the last couple of days here. We talked about charging objects and how objects get a charge. Beginning of the unit, we talked about how objects have a charge. We've been talking recently about how objects get the charge, how we charge objects. Two ways, conduction and induction. Okay, one of these ways, conduction or induction, never involves a transfer of charge. Which one is it? Conduction or induction? Never a charge transfer. Yep, Bryce? Sorry? Induction, right. It never, this is the never one, right? This is the never-neverland category of charging objects here, because it never involves a transfer of charge, and it also never involves what? Touching. The two objects never touch together when we're talking about induction. Whereas conduction always involves a transfer of charge, and blank involves touching. It doesn't always involve touching, but usually involves touching. We break down conduction into two categories. That's friction. Okay, we talk about maybe water molecules rubbing together in the clouds, causing a separation of charge. Okay. Friction rubs. Two objects rub together. Charge transfers from one thing to another. Charge transfers from one droplet to another droplet. Okay, in the end, the law of conservation of charge still holds. Charging by contact is that thing that we talked about the very first day of this unit. Okay, bring something nearby something else, finger nearby your finger, touch them, zap. We transfer physically charge from one thing to another because they touch or because they become close enough that it's as if they touch. Then we call that charging by contact, or sometimes just charging by conduction. Conservation of charge holds here too, because in the end, if I've got something that's +5 and something that's -5, touch them together, they're going to balance out to be 0 and 0. All right, this is the one that I really want to focus on, because this is the harder one, the whole induction thing. Here's a neutral object. Think, oh, it's the same thing we've done over the last few days. Yeah, it is. But you know what? I'm going to make it look a little bit different here. This time our charging object is going to be negative, but it's going to be circular. Does that affect things? It's always this rectangle rod that I bring nearby, right? Does it matter if it's circular? No, of course not. It's negative. It doesn't matter if it's circular or square or rectangle or whatever. What happens to the protons inside there? Michael? No. Well, they are attracted to the negatives, but they don't go anywhere, right? Yeah, they stay put because the protons are in the nucleus and they can't go anywhere. They want to go over there, but they just can't go over there unless they drag the entire atom with them, and that doesn't happen. So they stay put. What happens to the negatives? Look at what happens to the negatives there, the electrons. Good, they get pushed to the other side, repelled by that negatively charged object. So instead of having an evenly distributed bunch of electrons to give me a neutral object, I've got still a neutral object, but a separation of charge where one side has more negatives, the other side has more positives. How do I make that permanent? How do I make it permanent, Bryce? Yeah, ground it. And grounding it could involve literally attaching a wire or some kind of conductor into the ground, but it could involve something like this. Here's another object, another neutral object. When I touch that to the first neutral object that I had, the black one there, what happens? Well, the electrons that were pushed to the left side, we'll call it of object number 1, keep going into the third object, the thing that is basically acting as the Earth. So these negatives keep going into here. Now I've got a positively charged object there, right there, object number 1. And the other one becomes negatively charged, right? Separate those, and look what happens. It's now a permanent charge, a permanent negative in this guy, and a permanent positive in this guy. What do you call that? Conduction or induction? Nathan? Why do we call it induction? Didn't the electrons transfer from object 1 to object 3? They did, didn't they? Didn't we say conduction always involves a charge transfer and induction never does? Why did you call it induction? Because permanent? Yeah, this is the thing that's important right here. Look, if object 1 and object 3 started off as being neutral, and object number 2 doesn't exist, then object 1 touches object 3, nothing happens, because neutral touching neutral stays neutral and neutral, right? No charge transfer takes place. But if I bring object number 2 nearby, it pushes the electrons from 1 to 3. There is conduction taking place there. There is absolutely conduction taking place there. But the overall process we still call induction, because the thing that causes it all, the thing that's causing this charge transfer to take place, isn't touching and it isn't transferring. So there is conduction taking place within there, but the overall process is still called induction. Does that make sense? All right, finally, Friday we drew a picture of an electroscope. Electroscope looks something like this. Do you guys remember what the purpose of an electroscope was? Chantal? Yeah, it detects charge. It doesn't tell us what kind we have or how much of it we have, but tells us that we have charge. There's the ball of the electroscope up here, okay, which is made out of metal, right? Why is it made out of metal? We talked about this on Friday, this device, right? But we didn't say why it's made out of metal. Anybody take a guess as to, or not a guess. We don't want to guess, right? Take a step. Yeah, it's a good conductor. If you remember at all how this thing worked, it's important that this whole thing, other than the surrounding part of it, is a conductor, right? So this ball of this electroscope is a conductor. The rod going down is a conductor, and the leaves are conductors as well, although they're really, really thin foil leaves, not heavy metal like the ball is or like the rod hanging down is. Really, really thin foil leaves. They've got protons in them. This has got protons in them. This has got protons in them, but everything's also got electrons in them. Everything's neutral, right? What happens when I bring nearby something that's, let's say, positive? What happens to the protons in there? What happens to the protons, Michael? They're going to stay where they are, right? Okay, just a few minutes ago we said protons, they want to go somewhere, right? They're attracted or repelled in this case, but they can't go anywhere because they're inside that atom. So they stay where they are. Kelsey, what's going to happen to the electrons? Yeah, they're attracted, right? That goes way back to the first day of this unit, right? Opposite charges attract. If this was a negative object we brought nearby, the electrons would be repelled down in. Okay, so let's look at these negatives that get pulled up there. Try to erase those. We had 4 of them. Now they're all up here. What does that do to the ball of the electroscope? Go ahead, Alex.
The ball becomes negative.
Yeah, I mean, there's still positive there, right? But there's more negative than positive. And what does that do to the leaves of the electroscope? Yeah, go ahead. Yeah, that first question was, yeah, you answered 2 of my questions actually before I even asked one. That's okay though. They both become positive because the electrons, they don't necessarily all leave like we have it drawn, but enough of them leave that it remains positive. And then if they're both positive, they repel each other. So we've just detected the presence of charge on that positive rod. Doesn't tell us it's positive because you get the same effect if it was negative, right? But in the end, there's charge there. We know there's charge there. Hey, one more quick question before I give you a couple applications of this here. If I stick a grounding wire over here, or touch it with something that's like a ground, right? What's going to happen? Michael, I'm going to ask you, what's going to happen to the protons? They're going to stay where they are. Good. What's going to happen to the electrons? Go ahead, Alex.
They're going to want to travel down to the ground.
Careful. What's doing the charging here? Positive. Okay, does that push electrons down into the ground?
Up from the ground.
Good, good. Okay, I'm glad you said that, actually. I am, because the temptation is to say, look, this positive is sucking these electrons up from the leaves and from here, right, and goes up into the dome. Well, they're just going to keep going as far as they can go, right? I mean, on one level, that makes sense. Okay, but if we take a step back from it, this is positive. It pulls electrons from anywhere it can, right? It sucks electrons from anywhere it can. This is the big source of the electrons. What's this? That's the Earth, right? That's the big source. So it can get a lot more electrons from there than it can from here. Electrons are going to end up going this way, leaving a whole bunch of negatives here. Eventually, those are going to start filtering down here as well. The leaves will still spread apart, but it's because they're negative now instead of positive. If you cut that, by the way, if you cut that ground wire, last question here, until I give you a couple more real life examples than this. If I cut that ground wire, and these leaves are spread apart because the extra negatives are in there now, what's going to happen? It's a new question. What's going to happen? You take a step back for a sec. Don't try to just, don't get tunnel vision here on this, okay? Don't be like, I think it's going to be blank. Take a step back and think about the answer to the question, why? Okay, and then try to answer the question for me. What's going to happen to those leaves? Kathleen? Yeah, perfect. Okay. Did you hear what she said? They're going to stay apart because, look, these electrons have nowhere to go now. They might want to go back into the Earth if I take this away, but they can't because I've cut the ground wire. So now it's permanent. They're going to stay there. Now, realistically, it's not going to be forever, right? Eventually, they'll drain electrons into the air, right? They'll discharge into the air, but it's going to stay there for an extended time at least. All right? Is that good? Well, this is new. Friday, we talked about the electroscope a little bit, and we talked about that being an application of this whole charging and stuff. This is a more, I don't want to say every day, because you're not going to see this every day either, but it's more real life at least, okay, a little bit more practical at least. This is what we call an electrostatic precipitator. Oh my goodness. That doesn't sound very real life, an electrostatic precipitator. What does an electrostatic precipitator do? What does precipitate mean? What does precipitate? Precipitation is rain, right? But where does that word come from, precipitation? Precipitate. Chemistry people. Yeah. Kinda, yeah. Take something out of, right? If in a chemical reaction a precipitate forms, you kind of take a little bits of solid, a little powder or something out of the liquid. In rain, you take water droplets out of the, right? Precipitate, something comes out of it. This is a precipitator, an electrostatic precipitator. What it does is filters air. In my furnace at home, I've got just a mechanical furnace filter. It's literally go to Costco, buy the furnace filters every 3 months, take the old one out, pop the new one in, and it mechanically separates the air from dust particles mainly. Right? Now, you can buy furnace filters that'll filter out really, really tiny particles, but it's still a mechanical process. So it's not great because it's still mechanical. Little tiny particles can get through the filter. Right? And then they go through your house, and you breathe them in, stuck in your lungs, and you die. No, not that bad, usually. This is better, because this works on electricity principles. Here's what happens. You got these green circles, which represent dust particles or pollutants of some type. They're neutral. these neutral dust particles are pushed through, probably by a fan. They're pushed through these blue, negatively charged rods. That's pretty hard for you guys to see from where you are right now, but these blue things are labeled negative. The reason they're negative, by the way, here's our power supply. And a power supply always has the negative end as the short end, the positive end as the long end. So the side of the power supply that's closest to these rods, these blue rods, is negative. The other side is positive. That means the blue rods become negative. So this air, including these green dust particles, get blown through these negatively charged rods. What happens? What happens when these, listen carefully to my question, what happens when these neutral dust particles come close to or touch these negatively charged rods? They what? No, think, guys, again, take a step back from this and think, okay, this is a day one electricity question. What happens when these neutral dust particles touch these negatively charged rods? They become negatively charged dust particles. They want to balance, right? The reality is they probably wouldn't balance, right? Because the dust particles couldn't hold as much charge as the rods could, but they'd try. So the dust particles would become negative. Look, these green dust particles are blue now. Blue showing that they're negatively charged. Now, these negatively charged dust particles continue to be blown through this filter, but now they're being blown through this positively charged grid of plates. What happens now? Negatively charged dust particles being blown through with the air, these positively charged plates. Good. Perfect answer. They're being attracted to, and then they stick to these positively charged plates. What comes out the other side? What comes out over here? Same thing that went in, minus the dust particles that got stuck to those plates. Okay? This is a better process because it doesn't matter how small the particles are, right? If the particles become charged, they can be stuck to those positive plates. In my furnace filter at my house, okay, if the particles are too small, then they're going to go right through the filter. That makes sense? Got another one for you. Let's pretend for a second this is my backyard. It's not, by the way. I don't live on the ocean, and I don't have a swimming pool. Used to have a swimming pool. One of those ones that's like 6 feet in diameter and about 8 inches deep. Didn't look quite like this. Don't have a metal fence around it either, but let's pretend that I do. Okay, this is my backyard. Got a metal fence around this beautiful pool, living on the ocean there. I want to paint my fence. I don't feel like painting my fence with a paintbrush because that's a pain. That takes a long time to do. So I want to use a paint gun. I want to blow the paint at it. The problem is, boy, that wastes a lot of paint, right? Because paint goes everywhere, right? It does a good job, but it wastes a lot of paint. The other problem is some of that paint, some of that extra paint ends up getting on the deck beside my pool, and some of that paint probably even gets in the water. I don't want that to happen. So I use a special kind of paint gun, a special kind of paint gun that has a charged rod inside it. Maybe that rod is negative, maybe it's positive. It doesn't really matter. Let's say it's negative. The paint comes up through this little tube here, through the paint gun, and then it goes past this negatively charged rod. I got a neutral molecule of paint. I got a negative rod that this neutral molecule of paint goes past. What happens? Bryce? Paint becomes negative. Paint becomes negative, right? All right, so the paint becomes negative. Now you got all these negatively charged paint droplets coming out here. This fence, which notice is a metal fence, what difference does that make? The real fence in my backyard is made out of wood. This wouldn't work with my fence. Okay, but it would if my fence was made out of metal, because metal is a conductor. This metal fence is attached to the ground. Right? It's automatically grounded. It's neutral and it's attached to the ground. This neutral metal fence will attract these negatively charged paint droplets. And then what happens to the negative charge? Paint droplets stick to the fence. What happens to the charge? It goes down into the ground. Right? What's the benefit of that? Have a look at this. Kind of looking at one of these fence posts from above. These paint droplets come out of the spray gun. Some of them hit it straight on. Perfect. Some of them go up here. Look, they're attracted. Some of them go way up here. Those are the ones that would go right through and paint the deck of my pool and ruin it, right? But those paint droplets, because the paint droplets are charged, get attracted toward this neutral object. So not only do I paint the front of my fence, I paint the back of the fence at the same time. Now, the reality is you probably have to go kind of touch it up a little bit from behind, probably, I would think. Okay, but the beauty of this is all of these paint droplets over here that miss the object now get sucked in towards the object electrically. Make sense? They paint cars like that too, right? Anything metal, they can paint like that. Why do they paint cars like that? I mean, they're painting it in a shop. It doesn't matter if there's, you get paint on the wall of a shop, right? Why do they paint cars like that? Because it's cheaper, right? In the end, if you don't waste paint, if you only use half the paint, it costs half the price. All right. I want you to take a look at 2 multiple choice questions here right now at your desks, and we'll take a look at them in about a minute and a half. 37 and 38, please. All right, what do you get for question number 37? It says, the bottom of a thundercloud usually becomes negatively charged. I don't know how well you can see that up on the board here, but the paper in front of you, you can see that the bottom of this cloud is negative. Doesn't matter how it gets that way. Okay, it's negatively charged. Before lightning strikes, the charge on the ground directly beneath the thundercloud will become what? Hey, what is, in my mind, probably the single most important word in this whole question? I don't know if I want to say the single most important word, but it's pretty important. Before, the word before the lightning strikes. Okay, when lightning strikes, electrons are being transferred. This is before electrons are being transferred. What does that tell you? This is before electrons are being transferred. I don't even care what the question is. What does it tell you when we know that it's before electrons are being transferred? They haven't touched and we haven't transferred. It means what kind of charging do we have? Induction. We know it's got to be induction because nothing has transferred yet. What's the charge of the ground become? Well, this is negative. The earth is neutral. What does it do to the protons in the ground? Michael? Stay where they are. What does it do to the electrons? Electrons get pushed down here, right? So the part of the ground that's directly beneath becomes positive. Positive by induction. And this is the same question that we've been reviewing, right? Draw the picture. Okay. Got a neutral object. Got a negatively charged object. What happens? The exact same question, right? 38. During the downward lightning strike, so this is when charges are being transferred. Right away, what does that tell you? Conduction, right? The charge on the top of the tree becomes, if you're transferring electrons to a tree that's neutral, the tree is going to become negative. So it's going to be negative by conduction. The answer is B. Got one more for you, and then we'll take a bit of a break here. Okay, what's happening here, guys? Student places a positively charged sphere near a metal rod. Both are on insulated stands, and the rod is grounded. What does that mean, insulated stands? Go ahead. The stands can't what? It sounds like keep a charge. They can't. A better word than keep. yet it can't transfer charge. So basically what we're saying is that these guys aren't connected to the ground. Okay? There's no connection to the ground. So honestly, they don't say that. You probably don't solve this question any differently. Okay? But in the end, this question should be solved differently if they are connected to the ground, right? We just probably wouldn't notice that. So they're not connected to the ground, except this guy is grounded, it says. There's a grounding wire right down there. What's going to happen to the charge, distribution of the charge on the rod? This is positive. Positives aren't going to move anywhere, so negatives are either going to go down into the ground or up from the ground. What's going to happen? Down in or up from? Up from, yeah. So this is going to become negatively charged. That means the distribution of the charge on the rod is negative at end X, and the electrons are moving onto the rod from the ground. Good?